Got a list of things that we're going to be covering. They're not really as individual as they sound because they kind of all blend together. But the main theme is that we're going to calculate probabilities. And the ones I'm calling theoretical are going to be the ones to do with rolling dice and getting cards, and we'll do a few of those again. Going to do frequency tables, which is, you know, somebody's collected an experiment and you've got frequencies and you're going to use them to calculate probabilities. That word there says categorical data. It's categorical tables in this case. We're going to use ands and ors in quite a few of these. We're also going to test for independence, and we're going to do that using conditional probabilities, and conditional probabilities will appear in these as well. So let's start off with an example of theoretical. We'll do a card one. So you could get a simple one like, what's the probability that you get a card that's a red and it's an ace? Now you have to be careful with the word and in statistics, and really means both. So this probability would probably make more sense if I just said, what's the probability that you got a red ace? Now, when it's a single card as it is here, the bottom number is 52, and the top number is how many red aces there are, and simplified fraction gets you that. Now, if we do slightly more complicated one, a conditional probability perhaps, I could say to you, what's the probability that you get an ace given that the card was a club? Now, when you get conditional probabilities, and you know it's conditional, that's the vertical line. I've overemphasized its length here. Then since you know that a club, that changes the world. So now there's only 13 cards it could be, and only one of those is an ace. If I asked you to do a OR question, and I said, what's the probability that it is greater than 10, or a face card? So you're picking one card from a deck of cards and you're trying to find out what's the probability that it is greater than a 10 or an ace card, a face card. And in those ones, you have to be careful that you don't double dip. What I mean by that is you count the same card twice. Now, since you're picking one card, you're good. So what you're going to do is you're going to find the number of cards that are greater than 10. Then you're going to add the number of cards that are face cards. Then you're going to subtract the number that is both those things. And this one's kind of a weird one, but it's still a valid question. Now, when I say greater than 10, I guess we have to be kind of clear here. I am meaning a jack, a queen, a king, or an ace. So I'm counting aces as being greater than a 10. They're worth more than a 10. So what was that again? Greater than, you can't use me then. So it's a jack, a queen, a king, and an ace. And there's 16 of those. And there are 12 face cards. And here's what makes this question a little bit weird. How many of those cards, right, or how many cards are face cards that are greater than 10? How many face cards are greater than 10? It's a little bit silly, but what's the answer?
Isn't it all?
It's all of them. So can you see in this question, you end up with just 16 out of 52, which I believe is 4/13. I'll do another one that isn't as weird. What's the probability that you get a red card, given that it's a face card? So this is what my working might look like. You find a number of red cards, you add the number of face cards, and you take away how many are red face cards, I guess. And it's one card deal, so it's still over 52. Well, we know that there are 26 red cards. Used face cards again, there's 12. Now this time, you have to think a little bit harder. How many red face cards are there? That's another way of saying both.
6.
Right, 3 diamonds, right? 3 hearts, 6 there is. So you got that guy plus that guy, take away that guy. I believe the number is 32 out of 52. If you divide the top and bottom by 4, you get 8 13ths. Are we good? So, and I've just said that one. It's okay. Should have said or here, but it's the right answer. Should have said. Now, how about frequency tables? So these normally come from data. So let's suppose we collected data from some kids, and this is their age. And what should we ask them? Right, so they can be 5-year-olds, 6-year-olds, 7-year-olds, and 8-year-olds. Okay, one more, 9-year-olds. And we went and asked them, does Santa exist? And got 3 of these guys, 8 of these guys, 11 of these guys. Let's be accurate. Young kids believe in Santa, and older kids less so. So we'll do a total. And then what do we get? 31, 42, 55. And so the question was, what's the probability then that you choose a child at random and they're 5 years old? So you find a child, what's the chances that they're a 5-year-old? Well, 55 in the bottom, and there's 13 of them. That's pretty much it. Now, I could say, what's the probability that you pick a child who believes in Santa and they're older? Well, I can't really say older, that's unrealistic. They're 7 to 9 years old. Well, in this case, it would be that plus that plus that. That's all the children who are 7 to 9 years old. So what would that add up to? 1924. Okay. Oh, people coming in. What about another one? Let's do the table going this way. I think of topics. Oh, found some data on some married couples, and we found out what the age of, say, the male was, and it was 19, 20, 21, 22. So I guess it would be young married couples. And you could be asked then, what's the probability that you pick somebody from this sample and they were 19 years old? Well, if you add them, I think I made it nice this time. Let's see, 10, 30, 40, 50. Yes, nice round number. So the probability that that married couple, the male in that married couple, was 19 years old, it's 5 out of 50, or 110. And you could ask questions like, from this sample, what's the probability that you pick someone who's older than 21 or younger than 22 or whatever it should be? Now, not all categories in these tables have numbers. You could have Royalist, Democrat, Republican. Very small choice. And you found some people and you asked them who they were going to vote for. And 5 were going to go that way. 27 were going to go that way. 18 were going to go that way. And you could just say, what's the probability then that you pick someone at random and they were going to be a royalist? That's who they were voting for. By the way, the total here is 40. Every single one of those questions I've done, the total goes at the bottom. If you're picking one person, the total goes in the bottom. So 40. And the top depends what you count. So here, if I count royalists, it's 5 out of 40, which I believe comes out as an 8. I could ask you for those who are not going to vote Democrat. So how many people are not going to vote Democrat?
23.
23, which is that one and that one.
Total is actually 50.
Is it?
Yeah.
Whoa. Yes, it is. Well cut. Actually, that makes the numbers much nicer, doesn't it? Can't really do n into 2350, although it's quite a nice decimal, isn't it? And it's a very nice percentage. And I haven't been doing much of the decimals and percentages, but if you get this answer, isn't it pretty easy using your calculator to make a decimal or a percentage? I think most of the questions tend to be fractions, from what I recollect. So basically, if you want to use frequency tables as we do here to get a probability, you add them all up, hopefully correctly, and that will be your bottom number. And then the top number depends on what they ask you. So let's do some ands and ors. Let's do some categorical tables as well. So I think I should do it in the order. So a categorical table is basically a two-way table, something like this. So let's suppose we collected data. I need another line here. And it was Scotland against England. So we asked some Scottish people something, we asked some English people something, and self-identified males and females. And the question we asked them was, do you like sci-fi movies? And they said yes or no. And 91 of these, 105 of them, 39 of them, 95 of them. So in a categorical table, you have two variables, in this case, what they are, Scottish or English, and what they are, male or female. And the numbers inside in this are those who said they liked sci-fi movies. So you can be asked questions like this. What's the probability that you choose a person from this study and they're Scottish? So The best way to kind of do a table like this is to add some totals. So I'm going to do the row totals. These add up to 196. And these guys add up to 4, carry 1, that's 10. 3, 4, 120, 134. Going down the way, this adds up to 130. And going down the way, I have actually a nice number, 200. So if you're being asked what's the probability that you choose a Scottish person, the number that you're going to use is the total number of people, in this case 330. And then Scottish people come from here, and if you add them up, you've got 130. Let's do some decimals. I mean, if you wanted a fraction, it'd be 13 over 33, but let's do decimals. 130 divided by 330, and we'll make the decimal to 2 decimal places. So it's that guy, and for fun, 39%. So the chances that you randomly pick from this sample a Scotsman is at 39%. That's the probability of doing it. What's the probability that you pick a Scottish person given that they were a male? Now, if you tell me that the person is a male, that changes the bottom number. In this case, isn't the bottom number, well, isn't the information coming from this row and the bottom number is 196, right? Since you know it's a male, you only use the information from the table that's to do with males. So the bottom number is 196. And on the top, there's 91 of them. So 91 divided by 196. And the answer that I get here is about 46%. So far, so good. So you can do conditional probabilities. I'm going to do another conditional probability here. What's the probability that you are a male given that you're Scottish? So from this sample, what's the probability that you're a male given you're Scottish? Well, since you're Scottish, the table now turns into those two numbers. And they add up to 130. And the males are 91. And that combination, 91 divided by 130, is 70%. Just this amazingly nice number. Now, if I asked you, are being Scottish and being a male independent events? So are being Scottish and a male and liking sci-fi, because all of them do, independent events? In other words, being Scottish doesn't influence whether you're more or less likely to be a male and like sci-fi. Well, the way that you test that is the probability of A given B the same number as just the probability of A? If that is true, then A and B are independent. Now, we've already done that, haven't we? The probability that you're a Scot given a male, right, this guy here, is 46%. The probability that you're a Scot is 39%. You see, they are not the same number. So these events are not independent. So being a Scot and a male who like sci-fi are not. Now, if you look at the data, what I'm saying is, aren't there more males than females who like, or more Scottish people than English people, if you want to phrase it that way? But isn't there a difference? You know, being a male and liking sci-fi is not the same when you're Scottish compared to something else. And so there's a connection. Okay, let's do another categorical. Very simple one. And let's just do, we collected information on people who smoke marijuana. This is actually what they should be doing. They probably are, I hope. And we're going to be very simple here. And we're going to do mental health. So you've got good mental health, right? You're coping well with society. You don't have too many down days. You know, you can function pretty well. Bad mental health would be, you know, hard to keep a job. You're all, you know, you feel depressed a lot of the times, right? You've got issues, right? So how you would describe or define them, we'll pretend someone's done it for us. And those who use marijuana, 15 of them are in that category. Those who don't use marijuana, 30 in that category. 25 here. 30 here. Now, if you just used the raw data, you might come to a wrong conclusion. You might, for instance, say, people who don't use marijuana, there's more of them who have got some bad mental health issue, right, than those who do use, right? That's just the raw data, isn't it? Bigger numbers is doing that. But that's not really the truth here, because do you notice that there's a lot more people in the sample who don't use it compared to those who do use it? And isn't that important? Because if you have 10 times more in one category than the other, shouldn't you just normally expect 10 times as more yeses in that category, whatever the question happens to be? And that's why we need to do conditional probabilities. It's a way of kind of equalizing your data so you're comparing like with like. So let's do that. The probability that you have bad health given that you use marijuana, and then we'll compare it to the probability that you have bad health given that you don't use marijuana. And by the way, these numbers are totally made up by me, right? Well, let's do the first one. Probability that you've got bad health given you use marijuana. Doesn't the world now just consist of that column? Since you know that they use it, this is where your data lives. And the number we've got here is 25 out of 40. Let's do that as a percentage. 25 divided by 40 is about 62.5%. Now, what about those in bad health, given that they don't use it? Now, that makes it this group. And that is 30 out of a total of 60. And that is 50%. Now, aren't we comparing like with like now? In other words, we've equalized the data so that we've taken into account that there were more in one group than the other, right? It's kind of balanced it out. When you look at it this way, can you see marijuana users are higher rate of bad mental health issues than compared to those who don't use it? Would you agree that's a fairer way to analyze this data? Now, let's check for independence. And simply, does using marijuana have any effect on having bad or good health? Right, that's essentially what we're doing. So all I need to do is, let's do the using ones. We've already got that number, but I'm just writing it down again. The probability that you have bad health, mental health, given that you use marijuana is 62.5%. I'm now going to compare that to the probability that you just have bad mental health. Right, when you're talking about this question, right, there's no conditional probability. The total is, the number that goes on the bottom is the total of all of these. So that's 40 and 60, which is 100. And how many of them are bad health? The answer is 55. And can you see that that comes out as 55%? And because these two numbers are different, can't we make the conclusion that smoking marijuana does have an influence on your mental health? And would you also agree that since it's bigger than this number, it has a detrimental effect? Because the effect could be that it's less, right? You have less mental health issues. But when you look at the two numbers, this is bigger than that. So they are not independent, right? They're connected in some way. And the connection seems to be that it makes it worse. So when you compare, if you want to do any kind of categorical data, this would be the data. And this is how you would analyze the data. And that's why they can write reports and say, what's Canadian Research Facility has found out that people who eat a lot of bananas tend to not have as much osteoporosis when they get older, right? Making that up, but that's how they collect it, right? They got people who eat a lot and people who don't, and then how many get, and bone issues and how many don't, and then a little baby table, and it's pretty easy to analyze. The last one of these categorical ones in. We can imagine that we've and have done ones like this. They've collected data on testing, right? So you test for something. And so we've got a group of people, some who have HIV, some don't, and you give them a test. And the test can be positive, or the test means you don't have it, right? Do you know that there's no test, at least in the universe I know of, except the guy's dead? And even that's kind of dubious now with machines that can keep you breathing, though you're clinically dead. There's no test in the world that's perfect. Would you agree that there are going to be some tests where they tell you one thing, but the truth is the opposite? So this is a little data to analyze this. So we took a group of people, some who had HIV, some that don't, and we tested them. And there was 120 people in this group, and there were 10 people in that group. And there was 390 in this group. And what should I make? And 30 in this group. So in this clinical study, there was 150, there was 550 people in it. I'll leave these totals blank because we'll use them anyway. So what's the probability that someone chosen from this trial actually had HIV? Well, the probability that they had HIV is 150. Right. Count that. 130, 85, 50. You add that, count on there. And that's about 24%. Okay, so in this particular trial, testing the test, 24% of the people were HIV, right? What's the probability that you test positive given that you do have HIV? Well, if you do have HIV, you belong to this group. And those who are tested positive is 120, which is 120 divided by 130, and that is about 92%. And then I'm going to try this one. Ten people out of 130. Right. So they do have HIV, but they were tested negative. And there were 10 people in that group. And you know that can happen if you're in the early stages of having AIDS, right? There may not be enough of whatever they use to detect it, right? The T cells, I think, as they use to detect this. Couldn't the test just not be sensitive enough to catch it? That's true about COVID. You know, if you just caught COVID 10 minutes ago and I gave you a test in the 11th minute, isn't there a good chance the test won't catch it? Right? You can't. So, yeah, that's reality. And that happens. And that ends up being about 8%. Now, when a test gets something wrong, isn't it called, well, I've a term, but the term I would use is false positive and false negative. You know those tests? A false positive says you've got the thing when you truly don't. And a false negative says you're okay, you don't have it, in this case HIV, when you do. Now, we've just found out that a false negative happens about 8% of the time, right? So for completeness sake, let's find out this one. So what's the probability that you test positive, given that you actually don't have HIV, right? The don't HIVs are these people here, and that adds up to 420, I believe. So it's going to be 420, and who tests positive in that group is 30. And so we have 30 divided by 420, and this ends up being about 7%. So the chances of you having a false negative is 8%, and the chances that you have a false positive is 7%. Which one of those two is actually, in reality, the worst situation? And I'm not talking about numbers here, I'm just talking about the practicalities.
The false negative.
Yeah, isn't a false negative much more dangerous to you than a false positive? Because a false positive just says, you've got this disease, HIV in this case, but you've got COVID, you've got cancer, right? You've got A, B, C, D, right? But it's false, right? So what's the worst that's going to happen is you're going to have a freakish time because you think, you know, you're going to die, you're going to be seriously ill. And then they don't just stop there, don't they? Then do other tests and they check other things. And then they say, okay, you know, sorry for worrying you here, but, you know, after further tests, you're fine. Right, that would be that would be happened there. Now, if you had one of the false negatives, couldn't that be much more dangerous to your life and your health and other people? Because you got tested and nope, you're fine. Right. When you weren't actually, right? When you had HIV or you had COVID or you had whatever the disease, or you had cancer. Now, okay, you can't catch cancer, but if you had the false negative, wouldn't you just go on with your life and the cancer would just keep growing? Because you're not being treated for it because nobody thinks you've got it. So in the big scheme of things, whenever they do a test, they almost always try to minimize this one, make it as small as possible. But life's annoying. If you make this one smaller, what do you think happens to the other error? It gets bigger. And it's a kind of seesaw thing, right? If you make this one lower, the other one goes up, right? And very often what these tests have is they have a spectrum of values. And then they put a little line and say, if it's bigger than this number, you've got it. And if it's less than that number, it's just a natural, you know, hormone level, whatever it is you're testing, right? And they can slide that in such a way that this will become really small. But in practice, if they make this like 0.1%, you end up with so many false positives that doesn't it just be an overload on the system? Imagine every single person who get tested for COVID came out as testing positive. Well, wouldn't that be a very small rate of false negatives then? But wouldn't the hospitals be full of people who don't have COVID, you know, wanting some treatment that they don't need, right? Or HIV or whatever it could be. So you can only make one of these smaller. And when you do that, you're going to make the other one bigger. And that's unfortunate. But that is just the way these things work. I haven't asked for any questions lately. Are we good? Is there anything I've said you're not comfortable with? I'm looking for my little list, but I think I've covered all the good ones. Oh no, I haven't. I want to do, here we go. I want to do some more you, ands, and ors. Stick to cards again, they're always the easiest ones to use. So, what's the probability that you pick a card and that it's red, or it's a king? So this is going to be an or question. So 52 goes in the bottom. It's going to be for an or, the number of red plus the number of kings, take away the number of boths. So that's basically how you calculate all ors, right? It's how many in the first group plus how many in the second groups, and then subtract all the boths. So 26 reds, 4 kings. How many red kings are there? Because that's really what I'm asking when I say both. How many red kings?
2.
2, yeah. So 28, interesting number, check it. 28, divide top and bottom by 4, 7/13. Now let's do 2 dice. It's a little bit different. When you roll 2 dice, there are 36 things that could happen. That's an awful lot of things, isn't it? But can you think of it? A 1 and a 1, a 1 and a 2, a 1 and a 3, all the way to a 6, and a 2 and a 1, a 2 and a 2, all the way to a 6. There are 36 of them. So what's the probability that you get a pair or a total of 12? Now, I've told you that there are 36 things, so we'll take that for granted. So we're going to find out how many times you can get a pair. That means, you know, a double 1, a double 2, plus the number of ways you get a total of 12. Take away the number that are both. Now that is going to be a pretty hard thing to count in some of these cases. The pairs should be easy. Out of the 36 things that can happen when you roll 2 dice, how many of those 36 are the same numbers, right? A 1, 1 or a 6, 6, that kind of thing. How many out of the 36 are the same?
Six.
Yeah. How many add up to a total of 12?
1.
And in this case, isn't that 1 a double 6? And so you end up with 6 out of 36, which is a 6th. Well, that gets us into the idea. There we go. I'll just change it a little bit now. What's the probability that you get a pair again? Or total 8. I won't write down all the pieces this time. There's still 6 pairs. How many ways can you get a total of 8?
Three, I guess. 6 if you want to count the reverse of each.
You want to count the reverse, yes. So here goes. So you could get, for instance, a 2 and a 6, and you count the reverse as a separate event. Imagine one of the dice is red and the other's green. That might make that similar. But then you could get, what, a 3 and a 5, or the reverse.
Mm-hmm.
Now, is it 6? Yes, you can get a 4 and a 4. Now, if you reverse a 4 and a 4, is it really anything different? Isn't it the same thing? So in fact, there's 5 of them. Take away, how many are both? Well, since I've got these here, how many of these are a pair?
1.
Just 1. So what you've got is 11 take away 1, so you have 10 out of 36, and that gets you 5/18. Do you see that when they get to more complicated situations, you kind of have to maybe figure out a way of keeping track of them? Because it makes kind of sense that you would think 6 was the right answer, but in this case, doesn't that one there count as a single event? Because when you switch it, it's the same 2 numbers. These are different because first and second are different. And that is the ORs. So let's do 2, perfect timing. Let's do 2 ands and call it a day. What's the probability that you are a red card and, what shall I do? A red card and a 10. So out of 52 cards, what's the chances that you're both?
2 out of 52. So 1 out of 26.
And we'll do a dice one then. What's the probability that you are, keep doing pairs, let's do something different, that you have a total greater than 10, no, make it 9, total greater than 9, and total less than 12. So when we're talking about both here, aren't we really looking for things that have a total of 10 or 11? Agreed? In the way that's counted. So how many ways can you get 10 and how many ways can you get 11? So here's my little guys, probably won't use them all. Let's start with 10. Give me a combination that gives you 10.
6 and 4.
So if you do 6 and 4, reverse it works. Is there any other way to get a 10?
5 and 5.
And that one doesn't reverse, agreed? Right, let's move on to the other tool, right? It was 10 or 11. So how can you get 11?
6 and 5.
And you are allowed to switch that one. Is there any other way of getting 11? So the total here is that there are 5 things out of 36. And say your last name. And your test will be available around about 1 p.m. today, actually. I think I've actually done yours, so I'm certain it'll appear at 1. That's about it. Have a nice weekend. I'll see you on Monday. I'll hang about.